Okay, and welcome back. In this clip, we're going to talk about reactions of alkenes, specifically when we're reacting them to halogens, and what the actual products look like. Again, quite simple stuff, but because it's a little new, we're going to go through it step by step. So, by the end of this clip, you should be able to describe these addition reactions of alkenes. And we're going to talk about and relate this to what you've learned at GCSE earlier, and that a test for alkenes is to use bromine water. So we'll talk about that also. So let's get cracking. Okay, now you'll recall possibly from the first clip that addition reactions are simply when we add a reactant to a unsaturated molecule to make a saturated molecule. So we're going from a double bonded species to a single bond species. So let's just talk about what the bond strengths of single bonds, single carbon-carbon bonds, and double carbon-carbon bonds are. Now, what I've got here is the bond strength for both a single and a double. As you can see, the bond strength for a single is 347 kilojoules per mole, an average bond enthalpy, and we've got an average bond enthalpy of 612 kilojoules per mole for the carbon-carbon double bond. Now you'll cover bond enthalpies after in the new year with in one of the modules. Essentially, it just means how much energy is required to break this bond. So we need 347 kilojoules per mole to break a carbon-carbon single bond, and we need 612 kilojoules per mole to break a carbon-carbon double bond. Right. So you'll also remember that from the last video that a carbon-carbon double bond is made up of a sigma bond and a pi bond, right? Whereas a carbon single bond is simply a sigma bond. So you can see that the strength of a sigma bond is 347. So what is the strength of a carbon-carbon double bond? Well, we can work it out. It's just going to be 612 minus 347 to give us 265 kilojoules per mole. So you can clearly see that 265 kilojoules per mole is less than, so this is for a pi bond. And you can clearly see that a pi bond requires less energy to be broken than a sigma bond, so it's weaker. Done. Right? A pi bond is weaker than a sigma bond. And when we're covering these addition reactions, what you'll see is that the pi bond breaks, but the sigma bond remains. So let's have a look at an example. The general equation for addition reactions, as you can see, we're starting off with a unsaturated, number one, and we're going to form something that's saturated. And let's have a look at that, okay? Essentially, all that happens is this. We form a product, we're breaking the pi bond, so we've only got a single bond there. We've got no more double bonds left, and all we've done is we've now got the addition of A and B. Done. So this is number two. Number one is unsaturated. Number two is saturated. That's all there is to it, right? AB is added across the double bond, but for A and B to make a bond, we need to break a bond, so the pi bond of the double bond breaks. Done. So let's talk about a specific example. Let's talk about hydrogenation. This is when we're adding hydrogen gas and a gaseous alkene over a catalyst, and this catalyst is a nickel catalyst, and you've covered this in GCSE. Again, it's nothing new, we're just going to have a look at how it forms. So the conditions we need is a nickel catalyst and a temperature of about 150 degrees Celsius, right? So I'm sure you can, just having a look back at the general equation, I'm sure you can deduce what happens in this case, essentially all we're doing is we're adding hydrogen and we've broken the pi bond. That is all there is to it. Okay, the addition of hydrogen is also known as hydrogenation, and this is all there is to it. We've gone from unsaturated ethene on the left, and we've made ethane on the right, which is saturated. Okay, so it follows the procedure. We've got two reactants on the left. We've got ethene and hydrogen, and it turns into one product. Okay, we're going from 2 to 1. Dead simple, nothing particularly difficult. It's the same as what we've covered in the general equation. So let's talk about the addition of halogens, because alkenes do indeed react with halogens, right, in a process known as halogenation. Okay, so we can react alkenes with, bromine, chlorine, iodine, and these will all react at room temperature, so we don't need any special conditions at this particular point. So let's have a look at what the product is going to be formed. Well, you know what? We know we're starting off with a unsaturated. We know we're going to produce a saturated, which means single bonds only. Right, so we're going to break the double bond. And all we're going to do is add a chlorine on each carbon. Done. We have now made 1,2-dichloroethane. 1,2-dichloroethane. This is saturated. This is unsaturated. We're starting off with 2 products and going to 1. So again, simple addition reaction. Nothing particularly difficult there. So let's have a look at the third bit. The second outcome, which was using bromine water. Now you should all be aware that when you add bromine water to an alkene, it decolorizes. The alkene decolorizes the bromine water. Now bromine water is let's see, have I got this actual color? Yep, we do. Is orange in color. But when we add it to, it's Br2 of course, and when we add it to a alkene, essentially we have a very similar reaction to what's shown above, right? All we have is, rather than, if we start off with an ethene again, but instead we add Br2, all we're going to get is this. And because the bromine has reacted in an addition reaction with ethene, and it's formed this product, 1,2-dibromoethane, which is unsaturated, the double bond is gone. So therefore the test for alkenes is, you know what, if it decolorizes bromine water, there's double bond there. Done. Okay, so I hope that was useful. It was simply the addition reactions of alkenes to different reactants, specifically hydrogen and halogens, and the second bit was all to do with decolorizing bromine water and using this as a test. That's all there was to it. I hope that made sense and I wasn't blathering too much. Yeah, I'll see you in the next clip. Thank you for listening.